we're going to talk about multiplicity, turning points, and then at the end we're going to do an application. So the first thing we're going to talk about is multiplicity. Multiplicity is the number of times a factor or a root appears in a function. So we give you a hint. You need to look at the exponent. Okay, so if we look at this example, it says graph y equals x times x minus 2 cubed times x plus 1 squared with your graphing calculator. So if we get our graphing calculator out and we type in x times x minus 2, and to get cubed you can hit your little caret, and we hit the 3 for cubed times x plus 1, and that whole thing is squared. If we hit zoom 6, if you zoom in, it's going to look something like this. So if we look at each term, in our function, well, to find the multiplicity, it says look at the exponent. So if we look at this term first, well, this is really x to the 1. So the multiplicity would be 1, because 1 is the exponent. So the multiplicity is 1. Okay, so next let's look at this one. We have x minus 2 cubed. Well, the exponent is a 3. So the multiplicity would be 3. So our last term, we have x plus 1 squared. Well, our exponent is 2. So the multiplicity is 2. Alright, so the next part says, where are the roots, zeros, or the x-intercepts? Those all mean the same thing. So we are going to set each factor that contains a variable equal to 0. So if we go up here, our first one that has a variable is x. So we can take x equals 0. And we set up here that it has a multiplicity of 1. So our next set, we have x minus 2. We're going to set that equal to 0. If you solve, you're going to get x equals 2. Well, we said that has a multiplicity of 3. And the last one is x plus 1. We have to set that equal to 0. If you solve, you're going to get x equals negative 1. And we said that had a multiplicity of 2. So if we go over here, on our graph, we can see that we're going to have a root or a 0, or where it crosses the x-axis, the x-intercept, at 0. So here's our one at 0. So that point right there has a multiplicity of 1. Our next 0 is at x equals 2. So it crosses the x-axis at x equals 2. And that one, the multiplicity is 3. And then the last one we said x equals negative 1 was a 0. So at x equals negative 1, it crosses the x-axis, which makes it a 0. And that multiplicity is 2. So let's talk about if we have an even multiplicity or an odd multiplicity. So the first one, if we talk about even multiplicity. When we have an even multiplicity, the graph will touch or bounce on the x-axis, but will not cross through, causing a max or a min. So when we have odd multiplicity, the graph will cross through the x-axis. So when the multiplicity is 3, 5, so on, the graph wiggles through the x-axis. So let's work through an example. Okay, it says find the zeros and their multiplicity. Will the graph cross or bounce at each of those roots? So the first thing they want us to do is find the roots. Well, to find the roots, we have to set each factor that has a variable equal to 0. So our first factor would be 17x. So we have to set that equal to 0. So if we take 17x equals 0 and we solve for x, we'd have to divide both sides by 17. Well, 0 divided by anything is 0, so x would be 0. Our next one, we have x plus 1. We have to set that equal to 0. So x plus 1 equals 0. If we subtract 1 from both sides, we get x equals negative 1. So then our last root would be x minus 8 equals 0. Well, to move 8 over, we're going to have to add 8 to both sides. So x equals 8. So the next step is to find the multiplicity. Well, to do that, we have to look at the exponents. So if we go back up here to this factor, we have 17x. Well, the exponent of that is just 1. So the multiplicity is 1 for that root. So the next one, we look at that exponent. Well, that exponent's an 8, so the multiplicity is 8 for the root of negative 1. So the last one, we have an exponent of 3, making our multiplicity 3 for x equals 8. So then the last thing we need to do is figure out what the graph is going to do. We want to know if it's going to touch or bounce, or if it's going to cross through the x-axis. So if the multiplicity is even, that's when it's going to touch or bounce. When the multiplicity is odd, that's when it's going to cross. So let's figure out what it's going to do for each of these. Well, let's look at the multiplicity of 1 first. Well, is 1 even or odd? I hope you know 1 is odd. So the graph will cross the x-axis. So the next one, let's look at the multiplicity of 8. Well, 8 is even. So if we go over here, if the multiplicity is even, it's going to touch or bounce. So the graph will touch the x-axis. And the last one, we have to look at our multiplicity of 3. Well, 3 is odd, so the graph is going to cross the x-axis. Alright, let's flip it over. The next thing we're going to talk about is our turning points. So turning points can also be called relative maximum and relative minimum. So if we have a graph that looks something like this, we can see that if we're increasing, we're going to have a max right here. So we will call that a relative max. At this point, we would have a relative min. At this point, we would have a relative max. And at this point, we would have a relative min. So let's just put an ordered pair on there. For this relative max, let's say it's at the point 324. And let's say this relative min is at the point -3, 4. So when we say the relative max or min, we say that it is the y value at the x value. And we're going to say that x equals whatever number x is. So looking at the relative max, we can say that the relative max, oops, that's supposed to be max, is, well, it says that we're going to say is at the y value. Well, if we look at our relative max, the y value is 24. So the relative max is 24 at the x value. So our x value at the relative max is 3. So the relative max is 24, which is the y value, at x equals 3. So let's do the same thing for the relative min. So we're going to say that the relative min is blank at blank. So let's fill it in. So the relative min is the y value. So we look at a relative min, our y value is 4 at the x value. Well, our x value is -3. So at x equals -3. So let's do an application. So it says that a metal worker wants to make an open box from a 12-inch by 16-inch sheet of metal by cutting out squares from each corner. So if we cut out squares at each corner, if it's a square, our length and our width are going to be the same, but we don't know what they are. So we're going to call them x. It's going to be x by x. So we don't know how big our corner that we're cutting out is. But we know this is a 16-inch by a 12-inch. So part A says write an expression for the length, width, and the height. Well, if we want the length of this would be 16. But if we're cutting out x right here, we don't know how big that is. We're cutting out part of a corner right here and part of a corner right here. So we're taking away x and x. So we're taking away 2x of that 16. So our length would be 16 minus this little piece and this little piece. Well, x plus x is 2x. So you're taking away 2x of that length of 16. So the width, we know the width is 12, but we're taking away a piece right here and a piece right here. Well, this piece is x and this piece is x. So x plus x is 2x. And the height, we don't know what the height is. So if we're cutting out a little corner in that box, the height we're just going to call x. So part B says use what you found in A to write a function for the volume. Well, volume equals length times width times height. So our volume is going to equal our length, which we said was 16 minus 2x, times our width, which we said was 12 minus 2x, times our height, which we don't know, which is x. So part C, find the maximum volume the box can have. So we get to graph on our calculator. So if you get out your calculator, and your y equals, you're going to enter your function. So we have 16 minus 2x times 12 minus 2x times x. And I'm going to hit zoom 6, but we're not going to be able to see it, so we're going to make our window go up so we can see the point up there. So I'm going to make my y max 200. I'm going to hit graph. So there we can see that we have a max. And that's what we want to find. We want a maximum volume. So we have to find our maximum point. So if we go to second calc, and we go to max, so we want number 4, and we want to take our spider all the way up as close as we can to our max. If I can find it. Looks like we're getting closer. There it is. Alright, I think that looks pretty close to our max. So now it says left bound. So hit left a couple times and hit enter and go back to where you were. Now it says right bound. So hit right a couple times, enter, go back to where you were. Now it says guess. So we're going to hit enter. So it says our max is at, if we round to the nearest hundredth, is at 2.26 and 194.06. Well, the 7 we rounded up to a 7. So if we draw that out, if we just kind of sketch it, it looks something like this. And we had a max right here. That would be our max volume. Well, that point was at 2.26 and 194.07. So the max volume would be our y value. So our max volume would be 194.07. And up here we're talking about inches. So inches, and volume is always cubed. So 194.07 inches cubed is the max volume of the box. So part D says find the size of the cutouts needed to get this volume. Well, we said that the cutouts, or the height, was x. So now we know that x is 2.26. So we said that the cutouts of this box was an x by x. So if x is 2.26 inches by 2.26 inches. So then the last thing we can do is to find the dimensions this would give the box, meaning the length, the width, and the height. So let's start with the length. Well, we said the length was 16 minus 2x, but now we know what x is. So we have 16 minus 2 times our x, which is 2.26. And if you go ahead and do that on your calculator, you're going to get 11.48 inches. So the length of that box is 11.48 inches. So let's find the width. Well, the width was 12 minus 2x. So we have 12 minus 2 times our x, which is 2.26. And if you go ahead and do that, you're going to get 7.48 inches. And last is our height. And we said our height was x. Well, our x is 2.26 inches.